Thank you very much, and I wish to thank all the organizers for the invitation to this conference that is extraordinary high level. My talk will be essentially about integrable systems and their connections to what? To combinatorics, to modular space. This is one of the important discovery for us, for people working in integrable systems, saying that in many cases, top functions of classical integrable system can be identified with partition functions of certain quantitative theories. This is the formula. Essentially, there's still, well, there are many examples, and my talk will be on some of these examples, but still such an identification requires, I would say, some better understanding. So, in this identification, the time variables for classical integrable systems are identified with coupling parameters in the quantum theory. My talk will be about computational aspects. So, given an integrable system, we want to compute tau, but actually we want to compute log tau. This I want to emphasize. Log tau is not partition function. This is free energy. Some of our connecting Feynman diagrams. Okay. So, what I'm going to explain is the following. Question, very simple question, very natural. So, given integrable system, given initial data, we want to compute log time. This is actually all what I'm going to do. Some examples. So, the first example, since there is GUE in my title, first of all, this is outline. So, I will first formulate the main statement about computing GUE correlators. Then, instead of proving immediately this statement, I first switch to modular spaces to our previous result. Our means this is all with Markov-Bertol and Young in various combinations. We'll switch to previous example about computing Witten-Kontsevich numbers, Witten-Kontsevich log tau for KDV. Since KDV, both, of course, in the first case, the integrable system is polar, that is, for Witten-Kontsevich is KDV. Well, both examples are simple, but KDV, I believe, is more well known for the whole. Because of this, my explanation, derivation of this construction will be done for KDV. What will be the for example, or there are other examples. Then some very briefly outline a kind of generalization for simple algebra, the so-called topological IDs. Then I return back to random matrices and explain how the same ideology can be applied to derive the formula for GUE correlators. And then lastly, some numerical observations, if you wish, some conjectural connections between random matrices and cubic Hodge intervals over modular spaces. So, these are what we're going to compute, the correlators in random matrices, GUE, and a Gaussian unitary ensemble. So, there's a Gaussian integral integrals. We measure the dm of the space of n times n Hermitian matrix, which shows it to be unitary invariant. Okay, so all correlators depend only on eigenvalues. Correlators ensure between eigenvalues of Hermitian matrices. Okay, so this is the definition, Gaussian integral. And I will mainly will be looking at the so-called connected correlators. You know, this using weak rule, one can represent the correlator as some of these are-called ribbon-oriented ribbon graphs. This is the idea goes back to 12th, beginning of 70s. But I will look at the connected, some of the connected ribbon graphs. Okay, so every such correlator, is connected, in both cases, is a polynomial in n is the dimension of the Hermitian matrix, integer coefficient. This integer coefficient have some important combinatorial meaning that enumerating ribbon graphs with prescribed topology. Because of this, a lot of people went to this picture that they copied from the old paper by the 66 counterpart. This is a ribbon graph with one vertex, valence 4, and it has genus 1. It cannot be put on a sphere, it can be put on a torus. This is the meaning of the genus. So, now this statement, and our recent paper with the Young, I consider the first statement for one-point generator. We consider the following generating function that usually people consider study a lot in the theory of random matrices. This is the connected correlator dependent on parameter lambda, expanded when lambda goes to infinity. Okay? Then this is the formula of the generating series. You can expand, compute the coefficients and obtain your one-point correlator. Well, this f is a hypergeometric function, but you see, it is well known if one of a and b in hypergeometric function is a non-positive integer, then it is a polynomial, so-called hypergeometric polynomial. Okay, so all these one-point correlators are expressed in this way in terms of this hypergeometric polynomial, very explicitly. Okay. Now I will proceed to multi-point correlators to two-point correlators. To this end, I will introduce the following 2x2 matrix value series where the same hypergeometric polynomials are the interest of this series. Call it Rn of lambda, and they depend on the integer. So then, the formula for the two-point correlator is the following. First of all, I again consider correlators between traces of resolvents. With function lambda 1, lambda 2, it can be represented with some, well, one term is missing, sorry about that, the constant term, 1 of lambda 1, lambda 2 is counted twice. I should subtract it. Sorry about that. Anyway, there is a term of degree 0, degree 1, two terms of degree 1, and the term of degree 2. For terms of degree 1, the formula has already been written. So look, now the formula for degree...
The last term is just the power expansion.
Power expansion. Lambda infinity, actually, I wanted to say that I want to write the formula only for this term. Other terms are already written. This is the formula. and then we have to compute price of the product of those two Rn, subtract minus 1, divide over lambda 1 minus lambda 2 squared. The claim that this difference is divisible, okay, and can be expanded in inverse powers of lambda. Moreover, for any multi-point correlator, can be expressed in terms of the same matrix valued function, purely algebraic way. This is the formula for multi-point correlators. In this case, we do not need to subtract. We multiply for 3-point correlator between resulting. And these dots mean that I omit the lower degree terms. Okay? So, you multiply this matrices R of lambda 1, lambda k, take trace of the product, divide over this product of differences, and then take summation over all permutations of lambdas. We claim again that it is divisible, so there are no singularities where lambda coincide. It can be expanded in inverse powers of lambda. Then the coefficients are multi-point correlators. By the way, which initial data will be interested in? Initial data is very simple. 0 of x is equal to x. So the claim by Witten's conjecture proved by Consevich that if we compute now this solution, take the tau function of this solution and expand log tau and power series in times, then the coefficients of this expansion are some rational numbers that have important topological meaning. There's an intervals over modular space of punctured algebraic curves of genus G with an ordered marked points, intervals of powers of the so-called side classes. Well, I believe it was already explained in this conference many times what side classes are, well, and into detail. So you can, if you do not know, you can say that we are looking for this particular solution. My point is that that works here, that works for random matters, many other examples, that for computing tau function, instead of solving infinite bunch of nonlinear equations, we have just to solve one linear equation. And then everything will be expressed in terms of solution of this linear system or linear equation. Okay? Well, this about notations, sometimes for me it will be convenient to use notation from physics literature where these intersection numbers are called correlators to the quantum gravity, so tau observables, so this is your definition. By the way, I will not put the genus, so the genus is uniquely determined due to the dimension condition by the indices. So the theorem now is the following, one more generating function for correlators. Consider the following: lambda 1 will fix n. We take summation over I'm sorry, there's some nonsense written. It should be psi 1 to k1, psi 2 k2, psi n to k. Sorry about that. Well, and summate lambda's arbitrary parameters, double factors have to be inserted. For any n, I want to consider such a generating function instead of usual partition function. Okay? So again, it can be represented by the same, but instead of R, and for some reason they use M. 2 by 2 matrix M, again the same structure. You take product of matters is trace of product, you divide the product of differences, perform summation of a symmetric group, and for n is equal to 2 you have to subtract something to kill 4.
Lambda 1, 2, K1, right? Plus 1.
Pardon me?
In the upper side. Not just in the spring.
What is doing?
Lambda 1 to the power of 2K1 plus 1.
Okay.
No, usually it's 4 powers.
No? The formula is correct. The formula is correct except for this print here.
Well, that's the
Okay. And the formula from the matrix M of lambda in this case. So this formula for all genera for arbitrary number of set classes. This was our first step when we apply this ideology that I'm going to explain now. How to derive. I will derive this formula and then I briefly outline how to derive to deal with other examples. The derivation is based on the following.
The correction term for n equal to 2 is for any g?
It doesn't depend on g. Excuse me. Does not depend. As well as summation, I forgot to say, the summation over all genera. But the genus, the g is specified by its condition, dimension condition. Okay?
G is
There is no G on the right hand side.
There's no g on the right hand side. Then there's summation of all genera. There's no perturber, no recursion. Form of all genera. My lemma is a metric lemma that should be known, I would say, like 40 years ago, in the geometrical system. But now it fixed arbitrary solution to KdV. It writes the formula for the tau function for this solution. But for log tau, expansion of, we want to put simple logarithmic derivative of arbitrary order for given k1, kn as function of times. So because they can call them also correlators. And again, for notations from physics literature, with double angle brackets, like the correlators depend on the couplings or the times. Then the claim is that we form a degenerating function, but it now depends on times and on independent parameters lambda. The degenerating function can be expressed by this universal formula in terms of the so-called matrix resolvent of the Lax operator. So in my talk there will be the word resolvent appears in two different senses. Resolvent in the matrix and resolvent. This name was introduced by Gertrude Dicker for this matrix that I will define on the next slide.
So it's for KdV?
This is for KdV. What is resolvent? Very simple. Take the Lax operator. Write in matrix form. Look for matrix R, this script R, that commutes with Lax operator. Okay? Test ray 0, and I will normalize the condition determined as minus lambda. So, you see, when you have a linear operator, you can consider this many in various representations. But the most convenient is the joint representation. In this case, we have a way to nonlinear normalization of solutions. So the claim is that with this normalization, you have unique solution that can be expanded inverse powers of light. This is
Can you give a hint how to prove all these statements?
this statement.
No.
This is what I'm doing. This is what I'm doing. So first, this is one known statement. If you apply this in the definition, you obtain that all entries can be expressed in terms of this corner, R, and this derivative, and for R that exceeds in numerous powers, it begins with 1, due to normalization, okay? You have well-known linear equation that is so well-known that I don't want even to comment. Oh, by Hamiltonian recursion can be obtained. Even the KDV flow, I believe the simplest recursion procedure if we want to compute KDV flow, it's not the fractional powers of like this procedure. Much simpler. So this is first few coefficients of this matrix result. Of course, it can be represented as also products of eigenfunctions of Lax operator. But it's not convenient. Much simpler to compute directly. Anyway, the KDV hierarchy in different normalization without these double factorials can be written in terms of this coefficient in such a way. Capital T is another normalization that differs from the Witten conservation normalization by the double factor. Okay? Now, so, I forgot to say, due to uniqueness, if the potential of the Lax operator depends on times, according to KDV hierarchy, also the resolving depends on times. Okay? Consider now the generating series around this independent parameter. Simply the decay with respect to the standard normalization or double factorials with respect to non-standard normalization. What is dependence of the resultant on the time? This is this one-line computation. This is one well-known formula that was discovered and rediscovered many times. There's a you see, the regular R is one entry, 1-2 entry of the matrix script R.
Yeah, that's exactly right. But I just mean that either it comes like a miracle or it comes from.
Not a miracle. I don't know what means miracle. Witten-Katzevich theorem is a miracle, let's say.
It's come from geometry.
Okay, but this is much less miracle, let's say. Okay? Anyway, this is one-line exercise, really. I knew this since I should write in my PhD, that it was already some years ago. So now, consider the following function F2, trace of the product of this matrix involvement, this script R, matrix is 2 by 2, some type fraction divided over lambda minus mu squared. First of all, we see using this normalization, easy to see the numerator vanishes on the diagonal. Indeed, the trace of R squared is what is minus 2 times the determinant, so it's equal to 2 lambda. And this also on the diagonal is equal to 2 lambda. Okay?
Because of order it is 2 because of this.
Because of same, yes, because of the same. Now, using this equation for this right corner, you can compute this, maybe requires two lines. Compute introduce one more independent variable nu. Compute derivative of this function with respect to number nu, the generating series all time derivative. We obtain the following expression written here. Now, look at this expression. It requires maybe from 5 to 10 seconds to realize that this expression is symmetric in lambda mu nu. Symmetric. What it means? F2 is symmetric lambda mu is derivative are symmetric in lambda mu nu. You have equality of mixed derivatives.
And there is no derivatives there, just R, right?
Just R. But well, if you go on the blackboard, so from the symmetry you obtain the J, the K, the C from double KJ, and symmetry of the CIJ. That's it. You apply for parallel twice. That's it. Okay? Therefore, there exists a function called a clock term, the coefficients of expansion of F2, are logarithmic derivative of this function. This is my definition of tau function.
So I thought you started with the tau function to find the x.
No, I didn't start. I started from a solution. From a solution.
So you
Okay? Solution, then, so the main step start from compute the matrix resolver, compute the F2, and then you got a definition of tau function. Of course, there is some freedom up to multiplication of tau by exponential of a linear function. But this freedom has to be fixed in a separate question.
you can you define tau function, for example, also for Tauber hierarchy in this way?
Of course, this is about random matrices, what we do. And many other examples. Then, how do we write a big link about the formula the Forbidden Getsevich? So, this logarithmic derivative for tau that we got on the previous in the main lemma, and arbitrarily given point in the space of time. But we're looking at the logarithmic derivatives at the origin. Take the coefficients of expression at the origin. At the origin, one all times are set to 0, then u0 of x is equal to x. This is the initial data. So what remains to do? Remains to compute the resolvent for the given initial data. So I copied again the equation for resolvent. And now this is my lab separator. This is the matrix form of the area operator. You solve now this equation, one by John. It's better not to use area function, but solve directly, recursively. You obtain this 6k minus 1 double factorial and so on and so forth. This is about building concept. A generalization for an arbitrary simple algebra with, by the way, I forgot to say, this comment about bispectrality, since essentially everything depends on combination lambda minus 2e to x, we can replace equation in x with equation in lambda. This is what I mean about bispectrality. But now I'm a little bit less enthusiastic about this idea of bispectrality. random matrices we do not have any bispectrality. Okay, but here what we do, simple algebra, we now write what we call topological ODEs. First I begin with the simplest example of A n time, so the algebra is n plus 1. This equation for matrix valued function m of lambda, values in the algebra, and capital lambda is the following matrix. System of ODEs with coefficient linearly dependent on lambda. How to select the solution? There are too many solutions. We need some particular solution. So, back to a cell 2 example, to KDB example. This is my topological E, that's matrix capital lambda. M is now ABC minus M. Spell out this equation. Again, A, C can be expressed in terms of B, and the derivatives for B were obtained third order linear differential equation with coefficient depending on lambda. The space of solution has dimension 3. We want 1. How to choose? Read this as a column equation for column ABC. System of ordinary differential equations with polynomial coefficients. Okay, we know, what do we know? We know that all solutions are entire functions on the complex plane. But in infinity, there is irregular singularity. How to study the behavior at infinity? Well, this is just basic of WQP. The first thing to look at is the eigenvalues of the coefficients matrix. Okay? And one second computation says that one eigenvalue is 0, and 2 plus minus y square root of lambda. For 0 eigenvalue, the solution behaves in a regular way, like some power of lambda. For this has exponential behavior. I am looking at the regular behavior. Well, when I say behavior, I have to be more precise. Behavior only in certain sectors of the complex plane. This is irregular singularity. All series will be divergent by the asymptotic series of actual solutions in some sector. Okay?
Can you prove that there's always a unique regular solution?
I will tell you. I will tell you in a minute. Actually, for any simple algebra. Okay? So anyway, this is solved now, and you obtain this expansion up to this harmonization factor, exactly the same 6g minus 1. The factorials that we use for Witten Katsevich. For how to solve, one more comment is that when we do not need to solve recursively, you do not need to use anything. The standard trick to solve this ordinary linear differential equation for this type is to use Laplace transform. Now, so B is Laplace transform of some beta of x independent variable. After this, triple derivative becomes multiplication by x cubed. First derivative and lambda becomes first derivative and x. Apply first order for the, you can immediately solve. Really simple. You obtain then this solution. Exponential x cubed over 12 divided over square root of x. You obtain such a representation, you expand exponential in series, integrate term by term, obtain what you wanted. Okay? So this is our topological D, and this is what we call pure topological D. So sometimes it is more simple to solve U, sometimes even all this. And on the U side, you see you have an actual function. On the original side, you have just formal series. General case for simple algebra will be brief. You have to please stop time. The algebra basis of simple roots. EIF are wide generators. In this case, this is the definition of capital lambda. In this case, an element of the corresponding loop algebra, where E0 is the lowest weight vector, correspond to the negative highest root. Look now at the centralizer of lambda, I call it lambda 1. It is known, old result by Katz, that the centralizer can be generated, spent up to multiplication by powers of lambda, spanned by n, where n is the rank of the algebra by some n elements of the degrees. The degrees are equal to the exponents of the algebra, where n1 is the first exponent 1. This is just about principal degrees. Principal degrees, hence this EI all have degree 1, and lambda has degree h, where h is the Coxeter number. So lambda 1, because of it, has degree 1, and all other degrees are the exponents. So this is our theorem with Marco Bertolli Dion about the answer to the question of matter, that there exists a canonical basis in the space of regular solutions that have the following form: some fractional power of lambda small, then this, well, it should be lambda alpha, I changed the notation, plus terms with negative powers of lambda small, and the claim is the degrees. It is convenient not just to expand in usual degree of lambda small. It is convenient to expand with respect to the principal degrees. And with every term, the principal degree decreases by h, by the Coxeter. This is the basis, standard basis of regular solution. Okay? Now,
in which sense the basis is canonical?
yes, this is a good question. Really good question. How to normalize? There is some freedom, of course. This freedom was for us the main headache when we studied the connection with these quantiles around Witten intersection numbers. Okay, actually, what we this I will formulate in a couple of slides of our statement. Actually, so far we are sure about this connection only for A class, where these intersection numbers are just higher spin intersection numbers. Since for other systems we could not find sufficiently enough examples of these numbers. Thank you for your example. This is really important question. So my canonical, as I canonical, depends on this basis and this centralizer. Okay, and the basis some freedom in the normalization. And for D type or D2K, there are also some additional freedom in the choice of some two-dimensional based on two-dimensional subspace. So this is here. There exists all this essentially now from the infrastructure of hierarchy, where times are labeled by 2, and this is alpha k. So you take this basic, we call this again matrix resolvent, the n of them, and I'm sorry, again, this mess in addition. The previous rank was n, now the rank is l. No, okay? then n is the number of factors. Okay, so here we take the case of products of this matrix resolvent, dependent of indices, divide the products of lambda, symmetrize with respect to all permutation, and subtract some term for n is equal to 2 to clear the pole. Here the trace are just trace of the products in the joint representation.
What does it mean that you have a Q-n and then between brackets ID, ID?
And the same result of the same.
Thank you.
Connection with Punjab's Rowan and Whitman invariance, so what they invented nice name, quantum singularity theory. I don't have time to explain what it means, so the simplest case is A-type, where the quantum singularity theory is just you have to take some root of the canonical bundle, consider the model space, if you have a branch of a root of the canonical bundle twisted by some blind bundle sitting at the markings, to obtain some covering, and essentially intersection numbers of these coverings are within higher spin numbers. And Punjab is one, they obtain the generalization of this construction to other root systems. Well, it depends on some choice of some there's additional freedom. I don't want to enter into the details. So the claim is that we modify this as the correct normalization of this topological ODE. Well, essentially what we did, we looked carefully at the old Witten's paper, the normalization, and we realized that the way they define this is purely, so far, experimental observation, but since the Witten conjecture now, it has already been proved by Schreiber and Bonk and Father, yes. So this, for any case where we're sure that our claim is completely justified. And we hope that the same normalization, by the ability to check that this normalization is correct, we have to think how to normalize the basis in the centralized capital London. Back to random matrices, so you can imagine that it's not very difficult to apply the same procedure to computing, to derive this formula for multi-point correlators, but instead of KDV, we have to work with column. Okay, this copies from the previous. I want to just a reminder why we're interested, since, for example, if we consider the connected correlators of this type, it is polynomial in the dimension with integer coefficients. And these coefficients have very important combinatorial meaning, and number, in this case, number, you consider the dual to the ribbon graph. Yeah. Ribbon graph has valences of the vertices all equal to n in this case. For a dual graph, the graph is of polygons with m size, n bonds. So you obtain what sometimes they call mat on a surface of the energy made of k m bonds. In this case, there must be no lever. So because of this, this is integer. Okay. Anyway, this is something classical. So this is the partition function. There is, well, the affirmative coefficients are just times of the correlators. This all result in median of 90, and for the case of even polynomials, this was already even known by written. For this is just a reminder of what correlators in this name correlators is used often in many different sense. So these classical correlators on lattice infinite, in this case semi-infinite, of particles P and Q coordinates with exponential correlators. In this case, the difference, the approximate is different second order period. That we can do psi action on a function psi and function on the lattice. And these are derivatives in time and explanation. And eigenvectors are orthogonal polynomials. We can denote the harmonic orthogonal polynomials with this way. All my intervals in this, the partition function orthogonal polynomials are considered in the same, in the sense of formal expansion. I am completely just coefficient. I don't care about convergence. This is well known that orthogonal polynomials satisfy three-term recursion relation. That means they are eigenvectors of this class superior. And all this follows from the classical result by Bessich and that says the partition function can be represented as integration of eigenvalues of Hermitian metrics, okay, up to volume, and volume is up to factorial volume of the quotient of the unitary group over the maximal torus. And there is some explicit formula. So now let me introduce the matrix resulted. I will be implicit. This I call copy of the formula from the first slide in terms of the coupled geometric polynomial. What is this series? It's again matrix resolved of the difference separated. What is the difference separated? It's written here. Why? Well, since you have to look at the initial data. Initial data where all couplings are set to 0. In this case, we have obtained a Gaussian integral, okay, and orthogonal polynomial is a Hermite polynomial. I use this notation P since my normalization of the Gaussian bed contains 1/2. So these P's are Hermite polynomials, monic Hermite polynomials, orthogonal with respect to weight with the weight e⁻ x squared. And this is the three-term recursion relation. I said that Vn is 0 and Wn is equal to n. Okay? Now you write this in a matrix form and compute the matrix resolvent. You obtain this formula and then you repeat all the procedure that I explained for the KDV. That's it.
And so this normalization with double factorial is not typical of KDV. It's the same for Tola.
I don't know why. And so it appears here. You see, I've already said all confusions are determined uniquely. Again, you specify the value of the trace of the determinant.
In my understanding, it's more interesting that you have all powers of numbers. Because usually we expect it to be some summation of all powers of numbers.
Well, it depends among the various square roots.
I still think that there is that's where possibly a small difference, as usual, is hidden with the standard
Look here
formulation.
at the gene of algebra. This is what you want to get. The fractional powers everywhere. So we just for convenience we calculate the fractional powers for 2 by 2. Yes. Okay. Almost finished, but following the pattern that was proposed yesterday by Janine, that I have to have about application, about puzzles. But I'm going to finish with some mixture of application and puzzles. More puzzles than application. Application in the sense when we played with these numbers, we did a lot of this exercise. We found some interesting observation that still on the level of puzzles. So let me just propose just one puzzle. By the way, I forgot this is the theory about correlators I copied from the previous, from the beginning. It's a real puzzle. So look now at the free energy for the so-called special cubic Hodge integrals. Okay, so the lambda already appeared in some talks. This is the total charge polynomial of the Hodge bundle over the modern space. On a Hodge bundle, the fiber is over the Riemann surface of G is the G-dimensional space of holomorphic differentials.
So this term does nothing to do with the length of the...
No, nothing. Sorry about that.
So many letters in the
So
alphabet.
it's Hodge classes, right?
Yes, Hodge classes. And the parameters PQR must be constrained by this condition. This condition. Well, the integrals of this type for the first time appeared in Marino Baffa paper. So this is about Gopakumar Marino Baffa conjecture about Chern-Simons string correspondence. It was the most interesting. They suggested some formula, essentially species formula that was then proved by Minister Lu with collaborators and by control Pande. This formula for computing this intersection. Not in this form, there is some denominators, anyway. We don't know how to express, but we're looking at the analog of the free energy for the corresponding cohomological field theory. Call this HPQR. You want to compare this free energy with the partition of the free energy of the GUE. It is now convenient for me to introduce, instead of variable capital N, to introduce this so-called top coupling, X, and small parameter epsilon, whether 1 over N, just to represent the partition function in the form of 1 over N expansion. It is important for me how to normalize a partition function. This volume, according to the first, on the previous slide, it was some product of factorials, they call Barnes G function. After such a substitution, I have also to replace the Barnes G function by what is a symplectic expansion. Okay? So have this series, we want to compare for this particular value P and Q. P is equal to Q. And we can say Q minus 1 over 1. By the way, I want to bring to attention, it is perhaps too low, that now I consider potentials only with even powers of them. Even. Okay? This is what we first observe by numbers, then we tried still, it is a conjecture, but it was what was the starting point? The starting point was idea in our previous paper was that you know you've done, recently finally published, that in certain Hodge classes, fixed Hodge classes like polynomial lambda, or we use components of chain character, or Hodge bundle, this provides one then the corresponding partition function will be the function for some deformation of KDB. And then we realize if we introduce this particular cubic Hodge class, then this deformation is it coincides with the called Volterra lattice, or discrete KDB. Again, we check this up to some high genus we do not prove so far. Okay? But, however, this is the first law of the Volterra lattice. Okay? Then, of course, it is well known that GUE partition function with even flows, and also, in this case, total lattice reduces to Volterra lattice. We have two solutions to Volterra lattice. There are not too many solutions, but the idea they should be related. They are, and this is exactly the conjecture. And the formula will appear in a couple of days. That up to a linear change of variables in Hodge theory are T's and GUEs. Okay? And there's bar change of factorials for convenience. After such a linear substitution, up to adding some quadratic polynomial S and applying this simple operator in X, and this two parameters coincide. Okay, again, checked up to genus 5. The last slide, I want to, if you have some time to do exercise, how to check this statement for genus 0. Genus 0 Hodge class is just psi class, the Hodge bundle is scalar. So the genus 0, H0, the same as Witten consideration. Then the formula in this case is well known, that is formula for the second logarithmic derivative. Now look at the same second derivative of GUE genus 0. This formula is less well known, but also simple. Log appears. You see, under the log essentially the same formula up to normalization. So the claim is, after the substitution I copied from the previous slide, this and this, the formula concept. This is a nice exercise. But have some fun.
Absolutely.
Probably have one. So there was a quite old result of Schwarz and Katz. They presented the fermionic representation of Witten conservation, our function. So the formula is more or less equivalent to that result.
Yes, thank you for the question. Actually, if you look at our first paper, we used Schwarz operator. Okay, so instead of solving directly the equation for the matrix resolvement, we use the array functions essentially properly, and then the Schwarz operator was needed to choose a very particular factor, normalizing factor for the array function. It was a quite unpleasant computation. Now we have got rid of it. We do not need them.
Great. So let's